Hello, everyone. We'll just give it a couple of minutes till the audience gets in and signs in. Thank you for joining us. As we go through this panel, feel free to ask questions along the way. The Q&A button at the bottom of your screen there, and we will look through those questions and ask the panelists as we go along. Okay, let's get started. Hello, everyone. Welcome to the second virtual welcome to the second virtual event in a series of talks that spotlight innovation within the Cockrell School. Our topic today is Inside Innovation, Advancing Healthcare Through Engineering. My name is Ruben Rathnasingham. I'm the Assistant Dean for Health Product Innovation at the Dell Medical School at UT. And I have the distinct pleasure of working with Cockrell School faculty, students, and administration to promote and support engineering solutions for health. Being an engineer myself, I love working with and learning from my peers at Cockrell. The three people you will hear from today are some of the most respected thinkers, researchers, and educators who are leveraging their expertise in engineering to improve the lives of patients living with a broad range of health challenges. Professor Ben-Yakar, who has put her extensive expertise in biomedical optics, microscopy, and automation to develop next-generation tools for surgery. Professor Deshpande, who has developed robotic systems that support patients who are working to regain their physical function and live a life with dignity. And finally, Professor Yankeelov, a pioneer in computational oncology, who's working to make sure that people who are diagnosed with cancer get the right treatment at the right time while minimizing potential adverse effects from these very effective treatments, but often very risky treatments. Before I hand it off to them, I'd like to ask the audience to pay particular attention to the motivation of the panelists. These are incredibly talented and accomplished individuals, and I have no doubt that you'll be blown away by their technologies. But what is particularly inspiring about their work is the dedication to translate their invention to a solution, to transform their novel ideas to tangible impact. You'll observe their focus on wanting to solve real problems by first understanding the problems and uncovering the gap that they can uniquely help fill. It's clear that their goal is to make the lives of the ultimate beneficiaries, patients, better. So with that, I'll hand it over to our first speaker, Professor Ben-Yakar. Adela?
Hi, Ruben. Thank you so much for the introduction. It's a great pleasure to be in this e-talk and to be able to talk to all our audiences who are interested in learning about our innovations. So next, I will share my screen so I can share with you some slides to guide my talk. So you have some visual aids and see what I am referring to. So my talk will be about one of my research areas at UT Austin, about ultrashort laser microsurgery tools. And I would like to present to you how we bring these specialized lasers as the most precise surgical tool into clinic. First of all, I would like to explain what is ultrashort, what is the pulse laser. So we are using these lasers that they have very short pulses. What does it mean, ultrashort? All of you probably experience lightning, and the first thing that occurs, you see the light, and a few seconds later, you hear the sound of the thunder. And the reason that you see the light first, as you know, is the light is fast, much faster than the sound, travels and propagates to your eyes. As a matter of fact, light, let me get my pointer. Light can travel around the Earth in 1 second 7.5 times. That's that fast. And in our lasers, your duration, each pulse is 100 femtosecond. They travel only 30 micron, which is the width of a human hair. They are that short. When the pulses are so short, what happens is that we can squeeze them into very, very high peak powers. You can take all the energy that distributed in the conventional long pulses and into very, very short pulses. It means that you have 100 billion times higher peak powers. Now, the advantage of it will be that you can use a very high peak powers with very small energies. That allows you to perform very precise surgery. As one of my colleagues says, you can basically take the energy that when a fly lands in your hand, and with this energy that you feel, you can perform the surgeries. So that's kind of very small energies. And with this, you can achieve high precision. And the reason is that with the conventional lasers, the way that it interacts with materials and tissue is through heating. It hits the material, it gets absorbed, it heats it and evaporates and causes all kinds of collateral damage, thermal and mechanical damage. On the other hand, with our ultra-short laser pulses, these are as you can see, these red laser pulses coming and interacting with the material or tissue in a way that evaporates the tissue in a matter of very, very short time and without depositing heat to the surrounding tissue. So it allows you to minimize the collateral damage. And in tissue, it will look like this. I'm sorry, I'm sharing some images. These are actually real vocal cord surgical tissues. This is the only image that I will show from the surgeries, but I wanted to clarify my point. With the conventional lasers, you can see this carbonization and scarring of the vocal cord surgeries. Our vocal cords are very delicate. Actually, lasers revolutionized the vocal cord surgeries because previously they would use knives and remove the entire vocal cord. But with conventional lasers, still we have a long way to go to achieve the high precision that ultra-short pulses lasers can offer. As you can see here, we can do very small incisions and very, very clean and very precise. This is the advantage of ultra-short lasers. So when we do surgeries in vocal cords, we can keep its functionality intact and remove only unwanted tissue. So if it's really so great, these ultra-short pulses, why it's not in the clinic? How we can translate it into clinic? It's challenging, but these lasers are in the clinic already in the eye surgeries. You probably heard about the LASIK eye surgery to correct our vision, and femtosecond lasers since 2000. Let me just hide this floating channel. Femtosecond LASIKs are in the clinic since in the last 17, 15 years, and they are used to help the surgeries and reduce some of the, they replace actually the razor blades to create this flap where another laser comes and shapes your cornea to correct your vision. And that femtosecond lasers help removing some of the problems of trauma to cornea and sterilization that razor blades induced. And that's it. That's the only place that these lasers are used. And one of the main reasons is because these lasers needs to be delivered through these microscopes, large microscopes, and the patients are brought into the microscope to perform the surgeries. And there is no other place that you can do surgeries except eye with this kind of technique. What the doctors need is a handheld tool where the lasers can be delivered in a way that they will perform the surgeries in a handheld flexible tools, which is quite challenging. And at UT with my team of students and graduate students, undergraduate students, and research fellows, we have been trying to miniaturize this whole microscope into handheld microscope that actually looks in the hands of my student as like a pen. And this is our solution, and we have been working on it already many, many years, overcoming challenge after challenge through bringing innovations. So just to take you inside this handheld probe, how it looks. So we need to bring the lasers in a specialized optical fibers. These are microstructure specialized fibers. And then we need to scan the beam with microelectromechanical systems. These are mirrors that they scan back and forth the beam. They are fabricated in the clean room, the way that they are fabricated your computer chips and phone chips. We need to make customized optics, like little lenses. These are 2mm lenses. We need to design them and fabricate them with special diamond turning machines. And this is a dime, it's 18mm compared to, just to give you an intuition of how small they are. So we are targeting two main clinical applications. Our motivation, as Ruben indicated, it really is driven by the application. One of the applications is one of our most delicate tissues, the vocal cords. As I mentioned, we will use these laser surgery tools to remove precancerous lesions, nodules, and polyps, like these small lesions. And the second very exciting, important clinical motivation is spinal stenosis. Spinal stenosis is a narrowing of the spaces within your spine, which can put pressure on your nerves that travel through your spine, right? So most often occurs in the lower back or in the neck and cause a lot of pain. As we age, all of us starts growing the little bones, and that has to be removed. There are millions of people suffering with this pain, including myself, that I have some bone spurs that at some point I need to get surgeries to remove to reduce my pain. There are 500,000 surgeries yearly done to remove these decompression surgeries, we call them. And unfortunately, these surgeries often suffer from high rate of complications. And one of the reasons is that the available tools to the surgeons. They use these mechanical tools, as you can see, these biting tools that they insert into your spine. This is your, you can imagine, this is an illustration. These are your nerves, and this is a bone that is growing right here. And they come and they bite, and they have to insert multiple times these tools to be able to slowly bite and remove and break, literally break these bones so that they stop pressuring your spine and reducing the pain. And obviously, every time that they insert, there's a chance of this damaging the nerves and unwantedly and or causing inflammation. So there is a poor intraoperative control and multiple insertions. So what our suggestion is, these mechanical tools with our laser surgery tools, where they can, in one insertion, this laser very precisely can cut part of the bone, and then they can be removed by suction. So we need to insert it 1 or twice instead of like 15 times. So, and they can be very small, allowing the vision of the surgeon to other parts so that we don't damage the nerves. As our doctors from Dell Medical School puts it in their own words, a cutting tool that could follow the endoscope could revolutionize minimally invasive spine surgeries. So that's our hope. We have still a long way to go. We are looking into robotics feedback to improve the performance, looking into fundamentals of laser tissue interaction, doing some in-depth studies, understanding how fast we can perform these surgeries. And the ultimate goal is to develop the prototype that we can bring into clinic for testing. These are the team members and my collaborators that helped me to pursue this research and funding, especially the CPRIT of Texas, that helps us to pursue these efforts. With this, I will stop here and take questions later on. Thank you so much.
Thank you, Adela. Next up, we have Professor Deshpande. Ashish, if you want to get started. I also want to remind the audience that please feel free to ask questions in the Q&A button that's on the bottom of your page, and type in your questions as we go along, and we'll address them at the end of the panel. Thank you.
Great. Hello all. Ruben, can you hear me okay?
Yes.
Okay, fantastic. Hello everybody. Thank you for joining us today. It's a pleasure to be here. Thank you for your time this afternoon. As was mentioned, my name is Ashish Deshpande. I'm also from Mechanical Engineering Department, Associate Professor, and my work, broadly speaking, is in healthcare robotics area. So let me start out by sharing my screen. Great. So I direct the Renew Robotics Lab, which I established around 10 years ago here at UT Austin, and our focus is on robotics for rehabilitation, including prosthetic and therapy applications. I'll start out by a disclaimer that I'm a co-founder of a company here in Austin called Harmonic Bionics, and some of the work I'm presenting, goal of the company is to commercialize one of the exoskeletons I'm going to talk about. So overall in my lab, we are interested in studying how humans and robots interact, and we are interested in that from the healthcare rehabilitation perspective. We want to help those who are surviving with amputation, especially on the upper extremity, hand and arm amputation. In the US, there are millions of folks surviving with hand disabilities. We want to help those people. We also want to help those who are surviving neurological injuries, including spinal cord injury and stroke. There are 1 in 10,000 folks surviving spinal cord injury and millions of stroke survivors in the US alone. Our goal is to, we are exploring whether robots can help in improving quality of life, improve their rehabilitation outcomes, and in general, create positive impact for the lives of these individuals. So we take in my lab an extremely interdisciplinary approach. We tackle robotics challenges and human challenges. So we are focused on not only the mechanical design and control of these robots, but also on the neuroscience questions and biomechanics and human factors questions. So we work closely with clinicians, we work closely with neuroscientists in the design and control of our robotic systems. So we sort of tackling science questions, we're tackling also the clinical questions. So we carry out testing in the lab, and we also do testing in the local hospitals. I'll talk about that in a second. The first, I want to talk about 3 projects, 3 robots. The first one is a robotic hand that we have designed in my group. This is a one-of-a-kind robotic system that is designed to one day help those surviving hand amputation. So we are studying from the human hand to design a human-like robotic hand that can one day help improve quality of life for those living with amputation. So this hand has human-like abilities to move, abilities to interact with the object. And ongoing research right now, I'm collaborating with researchers from University of Michigan to design control of these robotic hands using neural signals from the amputee's limb. This is a brand new area of research where we are where researchers in Michigan are working on a surgery where we can get neural signals. It's a muscle reinnervation surgery by which we can get neural signal from the stump of the hand. And then those signals will be fed to the robotic hand to achieve daily functions. Switching gears a little bit, I want to talk about neurological injuries, including stroke. Stroke is a huge problem in the US. Every year, unfortunately, close to 800,000 new stroke cases happen, and we have millions of stroke survivors. And many of us could say have experienced stroke closely through family experiences or through friends' experiences. Stroke causes severe disabilities, including disabilities of motor, that is our daily function, movement, speech, and even memory. My focus within that is on the upper extremity function, which is affected for 80% of stroke survivors. And unfortunately, with the current treatment, only less than 20% of folks recover their daily function of upper extremity. So that causes serious limitations, and folks are sometimes left to be in the nursing facilities for many, many months. And even after that, they're not able to recover and be active members of our community. Conventional therapy involves lots and lots of physical and occupational therapy. It's highly labor intensive, very costly. And because of the higher cost, we have shorter and shorter treatments given the higher cost. A lot of the therapies focus on function, which is great in one way, but also sometimes misses the mark by causing what's called maladaptation, as in you don't really work on the core problem of the disability and you are always left with that disability. And one of the issues there is that we don't fully understand from the neuroscience point of view, what is the mechanism of recovery. This is where robots can come into the picture. Robots can, because of the, if you design the robots well, we can give, we can have quantitative data, we can give lots of therapy, and that can lead to, also allow us to ask questions about the relationship between therapy and the recovery, leading to potentially novel therapy. With robotics, because if we design them well, we could allow for more therapy. For a lot of patients, they're not receiving the amount of physical and occupational therapy that they need for the recovery. And we can also have customized therapy that is focused on the patient's disability and their injury. With those goals in mind, my group has designed robotic systems. Let me pause that for a second. The first one I'm going to talk about is a robotic system called Harmony Exoskeleton. This is a robotic system we built here at UT over the last 8 years, and it's designed to move the shoulders and arms of the person. So let me see if I can show the video of my system. Some of the key features of our robot is that unlike any other system in the world, we can give full shoulder mobility that results in much treatment for daily activities. We have better control also, so that we can design customized therapy, including, and also we have two-sided system that results in bimanual training. Usually stroke affects only one side, but the neuroscience principles show that treating both sides together might spur recovery faster. Another system we have built in my group is what we call a Maestro hand exoskeleton. Similar to Harmony, this robot is designed to deliver physical therapy for patients to recover hand function. We worked with this system with stroke as well as spinal cord injury patient, and we have seen successful assistance of SC for spinal cord injury patient. In this case, one of the examples is a patient named Paul who has limited hand function. He hurt his spinal cord about 7 years ago, and he lost ability to flex his fingers. With our robotic system hand exoskeleton, we collected neural data signal from his arm, his own nerve signal, fed that into our robot control, and he was able to achieve many daily tasks with this robotic system. Our vision is that to bring, similar to what Adela was talking about, our vision is to bring this system from research lab to the clinic in the hospital setting. We want to create, we want to develop novel therapy using our robotic system. We want to create immersive training and rehab environment with our system. And as you can imagine, with the data we collect, we can also have kind of wider population level understanding of how treatment of its recovery. We can also connect with the other modern technologies such as virtual reality to create an kind of engaging environment with a robot and the potentially gaming environments. I'll stop there. I also wanted to show the group of people in my lab without whom this work would not be possible. And also, I would like to mention federal agencies who have supported my work, including NASA, NSF, and NIH. Thank you.
Thank you, Ashish. So to our last speaker, Professor Yankeelov. Sounds good. Control.
Hello, great. Can you hear me? All right, very good. Well, thanks for sticking around for the final installment of this EE session here. And let's get right to it. So in the upper left-hand corner here, we have a projection for what Hurricane Sandy was going to do to the Northeast Corridor about 8 years ago in 2012. And this prediction was sort of remarkable in that 3 days out, 72 hours out, the prediction for where the eye of the hurricane was going to hit land was correct within 72 miles. And this represented a huge leap forward in predictive accuracy for hurricanes. And you can imagine that this is a really big deal if you're trying to figure out how to evacuate on the order of 12 to 15 million people. So this was a really big deal. Now down here in the lower right-hand corner is sort of a cartoon of how a tumor grows. Over here, we've got tumor cell number expanding over time, how the blood vessels that are feeding the tumor are expanding over time and how they're changing, a proliferation map, so how rapidly these cells are proliferating or if they're not proliferating at all, and then a distribution of oxygen, which of course influences all of those things. And so the question that comes up is how come in the upper left-hand corner, we're getting better and better at this, and in the bottom right-hand corner, we really haven't made a whole lot of progress. People have written down equations for how tumors grow and respond to therapy for over 100 years, but it's had very little impact in cancer biology and certainly even less so in clinical oncology. So let's take some lessons from meteorology. Weather forecasting divides the Earth atmosphere into a fluid, and it's governed by these well-established things called the Navier-Stokes equations. The details are not important, other that they're built on known physics, and they're a couple of 100 years old, and people have worked with them for a very long time. So these forecast models solve these equations on a 3D grid throughout the atmosphere, and we use observations of the atmosphere to predict things like the evolution of wind, temperature, humidity, and the rates of change of these things. So you get that data, at least in the United States, from a set of 160 of these things that are called Nexrad radar centers. The Nexrad is just a contraction of next generation radar. So you've probably seen your local weather personality talking about Nexrad technology. That's what it is. And these are the sites throughout the country. So you make these measurements. And of course, there's also other land-based measurements, and there's also satellite measurements and so forth. And those measurements are then used to populate the Navier-Stokes equations to make a prediction of how the weather is going to go into the future. So our lab's working hypothesis is that we can use advanced imaging techniques, advanced techniques like MRI or PET or CT or ultrasound, these kinds of things, can provide the data to initialize and constrain predictive models of treatment response. So hopefully the metaphor is clear. Instead of using satellites, we're going to use medical imaging, and instead of using the Navier-Stokes equations to describe how fluid flows in the atmosphere, we have our other tumor equations that we're going to use. So here are examples of the types of data that we collect. This is magnetic resonance imaging measurements of blood flow. And you're looking at right here, you're looking at a sagittal cross-section. So you're looking at a woman from the side. This is a woman with a breast tumor. The nipple would be right here. Chest wall would be over here. And very red, dark red indicates very high blood flow. Blue indicates very low blood flow. So in the breast, which is mostly adipose tissue, that's storage, fatty tissue, there's no vessels there, so there's very little blood flow. But if there is a tumor, then there is associated blood flow. And so you can see in this case, this is a very well vascularized tumor, a lot of blood flow going on there. After one cycle of therapy, which is about 2 weeks later, you can see there's been this reduction in the number of red pixels. That indicates that blood flow has gone down. And then at the conclusion of therapy, there's no blood flow there at all. And so this tumor has completely melted away. And this is called a pathological complete response. This is a very high predictor of 5-year survival. So when the family gets this information back, this is time to pop champagne. This is a big deal. And so this person would be labeled a complete responder. Contrast that with somebody who, if you look closely here, there's maybe a little red ring of high blood flow right there. And then as we go on 2 weeks into therapy, if anything, there's been an increase in blood flow here. And by the time the completion of therapy, there's still a rather large tumor with a lot of regions for blood of high blood flow. And so this patient would have residual disease and they would be classified as a non-responder. Another measurement we use is as measurements of cell density. So given a section of space, how many cells are in that area right there? And MRI measurements have been developed to be able to help you map the cellularity across tissue. And so this is the same patient as this patient over here, same time points as over here. This is before therapy. This is after 1 cycle of therapy, and this is the conclusion. Now, the color scheme here is actually inverted. So when you have red pixels over here, that means that there's actually low cellularity. And when you have the blue pixels, it means there's high cellularity. But that's because the measurement we use is a measure of water diffusion. So water will diffuse around in tissue with some characteristic time constant. But if there's more barriers in there per unit space, if there's more cells, then water can't diffuse as far per unit time, and the diffusion value is small. And you get these blue values. But if those cells start to die and go away, then there's less barriers and water can diffuse further per unit time, and you get these red values. So again, you have this is an indicator of response. And again, contrast that with someone who has a non-response. If anything, there's been a reduction in the water diffusion, which means an increase in barriers due to cells. So an increase in cell density from here all the way over to here. So back to our metaphor, these two types of data, blood flow and cellularity, are going to furnish our quote unquote satellite measurements that we use to populate our mathematical models of how tumors grow and respond to therapy. So just like up here, this is a humidity map, basically a water vapor map of the whole planet right here. So this goes into a weather model to make a weather forecast. What we do is we take measurements of blood flow and cellularity, and a host of other ones too, but we'll focus it for blood flow and cellularity. Those go into a tumor model to then make a tumor forecast. So the idea is that we have these pre-treatment data, and we want to predict who's going to be a responder and who's not going to be a responder. And the whole point for doing this, we want to be able to predict this, because right now what we do is we assess this. Patient comes in, they're diagnosed with a solid tumor malignancy, they get high resolution, either MRI or CT. The longest dimension of the tumor is written down somewhere in a spreadsheet. Patient goes on therapy. Maybe they're looked at with MRI or CT at a midpoint, or maybe it's the conclusion of therapy, and we look at the changes in the longest dimension. And if the tumor completely goes away, it's a complete responder. If it shrinks by 30% or more, it's called a partial response. If it grows by 20% or more, it's called progressive disease. If it's none of those things, it's called stable disease. And those 4 sort of categories constitute what's called the response evaluation criteria in solid tumors, or RECIST. And this is used in every single clinical trial of a solid tumor, but it assesses response. It has it in the name, the response evaluation criteria in solid tumors. So you're assessing response. We want to be able to predict response, because if you can predict it, then you can intervene earlier and hopefully in a more intelligent fashion, rather than just looking at the end of the day and saying this worked or did not work. All right. So how can we use mathematical models to predict who's going to respond and who's not going to respond? Because if you can predict, then you can perhaps optimize therapy on a patient-specific basis. So here's sort of the flow of action that happens. We use the early time point MRI data to assign the cell number and the drug delivery due to the perfusion measurements. There's a whole bunch of other model parameters that we then use that we can then determine by fitting our data to that model. I won't drag you through the weeds on that, but if you want to talk about it, that'd be great. So at that point, all the model parameters are known because they've either been measured, that's the first bullet point, or the model's been calibrated to the measured data, that's the second bullet point. So now that you have all the parameters of the model sorted, you can run the model forward in time, and that's your prediction. And then you compare that to what was actually observed. So here, this is called the cranial caudal view. You're sort of looking down from above on the woman. Here's the heart right here, lungs, and here is, of course, the diseased breast right here, nipples right here, chest wall is right here. And so the idea is you have this at baseline, you have a measurement after 1 cycle of therapy, say, and you use these data to calibrate your model parameters. And here is a calibration of how the drug is being delivered through the vasculature. That's what all those little wiry lines look like. And then down here, we have an estimate of how the drug is being delivered throughout the tissue. And so from those sorts of things, we make an estimate on how the drug is affecting the therapy, is affecting the tumor. And so we have a predicted cell number. So this image right here is just sort of a zoom in of this over here at the conclusion of therapy. And we have that predicted number and we compare it to what is actually observed. So if you look closely, you'll see that in some cases, we matched pretty well what the tumor was doing. In other cases, we underestimated, right here, a prediction that's underestimated compared to what was observed. And other places we overestimated. But the general trend is not that bad. And this is what we're trying to use to be able to predict the spatial and temporal evolution of tumors. So this prediction, again, was done about 2 weeks into therapy. And this image over here is taken about 3 months later. And so that's the comparison we're trying to make. All right, so the bottom line is that this approach yields a correct prediction of which breast cancer patients will have that complete response versus ones that have residual disease about 87% of the time, which is not bad. But of course, there's room for improvement. So that's sort of a big chunk of what the lab is studying these days. A reasonable question is, why are we doing all of this? Because this is very expensive. It's very time consuming. These measurements are not easy. The computational modeling is not easy. So why are we doing this? The idea is that without a mathematical theory, we're left with trial and error. And so the metaphor I like to tell everybody is like, if you go back to 1961, when President Kennedy said we're going to go to the moon by the end of this decade, and we actually did that, that was, of course, a remarkable achievement. But that was all based on Newton's laws of motions, which were sorted out, or were first sorted out in 1687 by Newton. So we'd been working with these things for 274 years by the time President Kennedy said that. And you contrast that with 10 years later in 1971, when President Nixon said, now it's time for this country to put the resources into conquering this disease that we did for going to the moon. In 1971, we didn't have the F equals MA of cancer, and we still don't. And so we're left with trial and error. So imagine in 1961, we didn't have F equals MA, and we just built thousands of rockets and just shot them at the moon, hoping that one of them would get there. And we learned from each one of these iterations. That's kind of what we're doing in cancer. Without a mathematical theory, you're left with trial and error, and we call it the clinical trial system. That's being a bit overdramatic, but the idea is similar. All right, so the last slide here. If this works, what's this going to look like in 10 years? The idea is a woman's doing a breast self-examination. She knows something. She goes in. She gets her diagnostic mammogram. And you don't have to be a board-certified radiologist to know that this thing looks uninviting. It's spiculated. It's got these invaginations, so it's sort of invasive. Biopsy's done, and it is indeed comes back as a malignancy. Then the patient goes to full-body PET CT to see if there's any distant metastases. Then you get all this patient-specific data, lots of imaging things on cellularity, metabolism, blood flow, proliferation, etc. Of course, you have the genomic data and the proteome data, and that goes into a mathematical model. This is one of the ones that we work with, and this is our attempt on trying to build an F equals MA of cancer. And the idea is that this guy right here, this little K parameter here, is the proliferation rate. Whatever, all the different effects that are causing these tumor cells to proliferate or not. It's a very complicated mixture of patient-specific data, the stuff over here, and then whatever therapy you're giving the patient. So this is where I stop and I say, don't look at the screen, look at me for a moment. Although I realize that I'm not very pleasing to look at, but just work with me here for a moment. So if you look at me, if you have a model that can actually recapitulate how a tumor is going to grow in space and time, then you can use that model to then try a bunch of therapies on the computer for that individual patient. So you don't have to give therapies and then see how it worked out. You can do therapies on the computer and come up with a probability for the best therapeutic option, and then that's the therapy you give the patient. So you can try treatment 1, 2, up to N of them. You can try tens of thousands of combinations. You can try order, timing, all these things that you cannot do in experiments because there's not enough patients, time, or money to do this. But you can do it so long as you can pay your electric bill for these really amazing computers we have at the Texas Advanced Computing Center. So you have your model that can recapitulate the spatial and temporal development of how a tumor grows in response to therapy. You then have some confidence in it, and you're going to go populate the parameters with the patient-specific data, and then go and try N different treatment regimens with this model on the computer to then make an optimized patient-specific therapeutic regimen. At least that's the dream. So we've made it so far as to get a big chunk of the day that's required. We have models that are working on the order of 87% of the time for predicting who's going to respond and not, at least within the case of breast cancer. And now we're working on ways to try to incorporate in an intelligent way different therapeutic regimens to come up with alternative dosing strategies, alternative treatment strategies. And that's what I have. Yeah, so that's it.
Well, thank you, Tom. That was great. And also well done to all our panelists. It was excellent presentations. And I'm sure if we could see the audience right now, you'll be all seeing them giving you standing ovation. So thank you. Thank you all. We've got a bunch of questions, and let's start by fielding some of the most specific ones to individuals, and then we'll go a little broader. So there are a bunch of questions around the performance of the technologies, and also how broadly it can be applied. So, for example, Adela, there are a number of questions around some of the parameters that you can tweak to change the performance of your device, and then also how broadly can it be applied? Because I know you were applying this platform to other things beyond health, before you touched on health. So if you could speak to those two things, I think that would be great.
Yeah, well, thank you. These are really good questions. I look at the question and answer. Clearly, we have people who are interested in the technologies, and they are themselves engineers. So I'm quite happy with that. So these are all good questions, and really to the point. So there are several questions talking about the laser parameters. So what is unique in ultra-short laser pulses? The ablation process, the cutting process, is independent of the wavelength. What makes it so powerful? Because with the conventional lasers, or even laser manufacturing, where we use lasers for manufacturing purposes, they have to be tuned depending on the application to different wavelengths. So the way that these ultra-short laser pulses work, they don't depend on the laser wavelength. Whatever the wavelength that we use, we can use it applied to all the applications. And the limitation is that it's very precise. So it removes micron by micron. And what you need to, and then only ablates where you focus it, which is advantage. At the same time, you have to take care of it as if you want to cut the bone, you can ablate maybe 50 micron deep and it's out of focus. So you have to use pushing the probe into the, hold the probe in the place, but push the optics so it can cut deeper and deeper and deeper. But this is available technology, and for bone ablation specifically is very feasible. In soft tissue, it's a little bit harder, a challenging aspect to be able to cut deeper and deeper. So that's, I think, answers some of the question of the laser parameters and how the wavelength affect the precision. So we usually have what is called near infrared wavelength. So this is the common where we can create femtosecond lasers with quite the powers that we need. And yes, Ruben, you're right. Actually, I started my career, I was engineer, but I went to the physics department to learn about more lasers and their applications, and I fell in love with these short laser pulses. And I started using them as in the manufacturing, cutting glass, because cutting glass is very difficult. And they break, and you cause all kinds of damages surrounding with the lasers. And if you want to do precise cutting, you need to use femtosecond lasers, ultra short pulses, pulse lasers, and that's how I started my career. And yes, it's nowadays is used in the industry extensively. Even there were some debates going on how the iPhones are used. They are using in their fabrication, and there are some lawsuits going on between different laser companies and IP issues that they are using the femtosecond lasers to cut their own, displays and the LCD panels and everything. So, so I think, but independently, there are many companies that they can manufacture for you with high precision, femtosecond laser ablation, small, very precise features. This is at the moment, as the lasers are becoming cheaper and cheaper, this is becoming more widely used. Yeah, I think that kind of answers. And many of the questions. But so the reason that I fell in love with biomedical applications are because it can really impact the health and then create the most precise tool. And it's not only about the laser surgeries. Ruben, you asked if there are other applications. The same lasers and the same laser probes that we are developing, we can also use them for cancer detection. I can help Tom to do better predictions, hopefully. So we can, by lowering the energy, but using exactly the same concept, you can look inside the tissue and look at the autofluorescence. So you basically, tissue absorb this femtosecond laser pulses, very low energy pulses. You really need to reduce and emit light. And depending on what kind of light they emit, we can understand if this location that we are looking at is cancerous or not, without taking biopsies out, just bringing your probe and looking with the microscopy technique, looking at the tissue composition and decide if it's cancerous or not. So these are other applications. So there's a lot of applications that can, from manufacturing to diagnostics.
That's great. Thank you, Adela.
Sure.
So Ashish, similarly, around the robots, we're getting sort of similar questions around, you know, this looks like an assist kind of therapy as opposed to kind of an actual therapeutic, and how do you see that? And also lots of questions around where else could it be applied, all the way from Parkinson's to sports treatment and so forth. You want to speak to that?
Yeah, no, again, great questions, great audience, thank you. I think I kind of divide this in my head in a couple of ways. One is assistance versus therapy. So whereas you could say somebody has ability to improve, in case of stroke, ability to recover kind of their neural connections, and I see the word neuroplasticity being mentioned as well. So where they have ability to recover, so but the therapy is physical therapy. So you move the body in the hopes of creating new neural connections, right? So that's we are focused on, that's what I mentioned. But similarly, robots could be used as assistive purposes where the recovery may not be possible anymore, but you get the neural signal, whatever is available, to then accomplish the task. The robot is the assistive in that case. And sometimes they get mixed too, because sometimes assistance can help in recovery as well. So yes, we are tackling both of those in case of neurological injuries, stroke and spinal cord injury. There's also questions about how about other neurological diseases, and also even sports or traumatic injuries, like you hurt your shoulder, for example, right? Could be from fatigue, could be from chronic use, could be from sports injuries. Those are a little bit different, because what actually in some cases might be somewhat easier because it's a distal problem where you are kind of maybe it's a muscle strength issue. So robot could help in that case, and we are exploring that as well. But our current focus is on neurological, where the movement could cause neural growth. And that's kind of a big challenge, but also exciting challenge, where if you can really discover, right now, kind of as Tom was mentioning about old school techniques and how we need to kind of innovate on those. In case of therapy, we are using the same techniques for the last 100 years, right? Where if you had stroke or if you broke your shoulder, the therapy is the same, which is move your shoulder, but the problems are really different, right? Where in one case we want to do the distally, where you want the muscle to get strong. In the other case, you want to go to the brain all the way and spinal cord injury. So we hope, I'm tackling that, and we hope that we can have maybe customized treatment for stroke based on the type of stroke and the base of the person, other situations. So that's where we focus on, but the other things are possibilities, and I hope maybe, down the line, we can tackle bigger issues, and yet kind of the system, fundamentally, there's no limitation in using that for other challenges.
Great, thank you, Ashish. And then Tom, it's kind of similar threads with you. The questions coming in around this, obviously including some sort of machine learning, and can the models be improved and leveraging different kinds of data. And there's one question from someone from the oil industry, from the energy industry, who refers to doing something similar or wanting to do something similar in that industry as well. You referred to weather forecasting. Can you leverage technologies that have been used in other industries as well, like you have with weather forecasting? You're muted, Tom.
Fantastic. Thank you. Yes. I was just so excited to share my thoughts with the participants. Yes, so we definitely steal ideas. In fact, I've always sort of been interested in weather as a sort of as a hobby. And I was actually at the beach reading a history of weather, of meteorology. And I remember in particular, there was one paragraph that really seemed like it could have described the state of meteorology in the year 1900. And it really seemed like it could describe the status of oncology in the year 2010. And so we have stolen a lot of ideas from a meteorology. The whole idea of collecting a data set over the area that's going to be predicted on and making a forecast, and then more complicated techniques like data assimilation to update your forecasts, to make the hurricane paths, like we see now on the Weather Channel for Hurricane Laura. So all these ideas, all these computational techniques, we've definitely stolen. I do want to comment, I heard you use the four-letter word machine learning there, because you said obviously some sort of machine learning is happening. And so that is a big knife in my back that I will have to now pull out and hand back. So when people talk about mathematical oncology or mathematical biology or computational biology, almost everybody thinks of artificial intelligence and big data and that kind of stuff. And so we are on that complete other end of that spectrum. We have this perhaps naive view that everybody is a snowflake, and for a disease as heterogeneous as space and time as cancer, the big data approach is just not going to work. So we do not do any machine learning or big data stuff. We build what we call mechanism-based models that have biology and physics in them, and they're calibrated on the individual patient. So you put in the individual patient's data into the model to make a prediction about that individual patient. There's no training going on in another data set. And the reason I think that I feel very strongly about this, if whoever asked this question is interested in this, please email me. And I've written copiously on this, and I'd love to share it with you. What's the point? The point is that cancer is so heterogeneous because it's not just one disease. It's somewhere between 100 and 200 diseases. So someone isn't diagnosed with cancer. They're not diagnosed with breast cancer. They're not even really diagnosed with, say, triple negative breast cancer. Triple negative breast cancer is a particular subtype of which we now currently are aware of 7 subtypes. So, so it's so focused. So if you want to be able to make prediction on Miss Jane Doe who has that subtype of breast cancer, of triple negative breast cancer, you have to go and find a training data set of tens of thousands of people who have that subtype, and then all the different therapeutic options that could possibly have been given for that subtype. And that data set does not exist. In fact, I don't.
Tom, mute, you're mute.
At what point did I get muted?
In the last.
I think you hit the space bar, maybe.
Oh, okay, sorry, yeah. So the point is, I don't think that those training data sets are ever going to exist because the therapies are getting more and more targeted and the diseases is getting more and more specialized. So I think things like machine learning are really good if you want to predict how many Buicks are going to be sold in St. Louis next year, because there are a small number of 4-door sedans with a bunch of very specific features, and there's a large number of cities that are similar to St. Louis. But for diseases like cancer that are so heterogeneous across space and time and across people, I just don't think it's going to work out. So that was a very long-winded way of saying that we do not do machine learning. We have mechanism-based models, no black boxes, individual patients to calibrate models for the individual. Yeah.
Great. I was hoping to set you up for that. So we have a whole bunch of questions. I just want to tell the audience that if you have some specific questions, you want to get in touch with these panelists, feel free to reach out to Susie Winfield, who I think is the liaison for you. I do want to ask one question because I think it's important, and because we may not have time to go through more questions, but I think it's important. So there are more than 100 people in the audience here, and I guarantee you there are folks in the audience who are watching and hearing from you guys and wanting to help. So if you guys could think through, like, what is the one thing, there are lots of challenges for you to get from where you are right now to patient impact. If there's one thing that you would want to overcome that you think someone could help you with, what would that be in terms of your research? So Adela, if you want to talk about what do you think your challenge is, if there's someone in the audience who you think could help.
Well, at the end of the day, everything is funding, obviously.
Yes,
but especially bringing technologies into practice, biomedical technologies, biomedical tools into clinic is challenging and it's very expensive, right? So, but in principle, what we will need to continue working and having more researchers and graduate students working on these aspects, but trying to get NIH funding and separate funding to continue to support ourselves. But in my case, we are still working on the theoretical aspects of understanding how we can increase the surgery speed. Once we kind of learn all the aspects in the next few years, the technology is there, we need to translate it. But this is, at this moment, at that moment, the challenge is not anymore something that the graduate student can do. Like Ashish has established his company. There is some place where this is not anymore a PhD type of research type of project. It has to be translated, and a working prototype that can work in the clinic needs to be developed, and that requires a lot of investment. And this is a transition, what we call it in the academia, that of validate, right? So where there's a transition, so you do the research, but to get the clinic, you need a lot of funding to be able to leverage this. So, so this is where the startup has to be established, or a company has to pick it up to create the actual real prototype to get the FDA approval and test it in humans. So right. That we did get an NIH grant for the diagnostics part, and we are developing a tool that will go into in the clinic. So we are trying within the university still. We'll see how this is going to work.
That's great. Thanks, Adela. So Ashish and Tom, you have 1 minute each. So what's your answer?
I think I would second all of that funding, and I think we are working on testing on people, which is again expensive, really important aspect of all of this. So resources for that. And also, if folks are interested in kind of investment opportunity, I think folks with stomach and interest with the medical tech, which is Texas has a lot of opportunities in that, but you know it's a unique set of investor that come along. So
great.
Yeah.
Thank you. Paul?
Sure. At the risk of displaying all my cards, I don't have any experience in building small companies. We've got, with some of our technology, we've gotten to the point where we have now applied for patents, and we're ready to take that next step, but it's nothing I've ever done, and I'm sort of intimidated by the mountain of paperwork that has to be done in between that and teaching and running the lab and being if you got to see being a father of small children, it's a bit overwhelming. So if there's people who are interested in moving things from the bench to a small companies, that's the type of thing that I really need guidance on. So, yeah.
Great, thank you. Well, we're at time, so I want to thank you all again for the time. Wonderful presentation. Again, the audience members, if you want to get a hold of these panelists, please reach out to Susie. And this was a wonderful experience for me. Everyone stay safe, and I'll see you next time.